I'm allowed to.
Let me. You should be good now.
Thank you. All right, hopefully you are looking at my slides. So it's my pleasure to be here with you all tonight to talk to you about dark matter and the subtitle, The Invisible Nest of Galaxies. And I will talk.
You should be good now.
Legend.
Let me.
Can you all hear me and see me? Yes. Sorry, so
You should be good now.
great. Right. So I will be talking about dark matter and how it's related to the galaxy. So in this front page, what you're looking at is the structure of dark matter, which we'll go into more today. And here you can see pictures of galaxies of many different kinds. And so how these galaxies and how their origins has something to do with the dark matter is our focus today. So let's start with something that is close to us. So you're looking at the picture taken at the site of Blanco telescope in Chile. This is a view of a clear sky in the southern hemisphere. You can see the Milky Way galaxy, the center of the Milky Way galaxy on the right of the picture. You can also see the large and small magnetic clouds. In the southern hemisphere, when the sky is really clear, you can even see them by naked eye. The Milky Way galaxy is where our solar system sits in. And we are about 8 kiloparsec, which is about 20 kilolight years away from the center of the Milky Way galaxy. If we now are able to zoom in from this picture a little bit more, you'll be looking at something that we call the local group. The Milky Way galaxy that we sit in is here at the center of this, well, not the center, but at the center of this coordinate. You may be able to see LMC and SNC, that's the large and the small Magellan clouds that I just mentioned earlier. And you can see a bunch of other small galaxies that are close to the Milky Way. We'll get back to these small galaxies later. You can also see our neighbor, the Andromeda galaxy, or M31. The M31 is about 3 million light years away from the Milky Way. And we call these two galaxies together as the local group, which is where we our home kind of in the universe. If I now continue to zoom out more and go look outside of the universe, let's say if you have a very nice telescope, in this case, the Hubble Space Telescope, this is what you will see when you look out to the space. You see lots of galaxies. They're of different types. You can see this, or this ones, they're all galaxies. You also spot a few stars. Now, to be clear, the star and galaxy that I'm looking at in this image are at very different distances. All the stars are local to the Milky Way that you're looking at, and the galaxy is much further away. They are outside of even our local group. In the previous picture, you saw the Milky Way M31 forming the local group. The galaxy you're looking at is like much further away, billions of light years away from us. You also see there's not much there's not much else beyond the galaxies and the stars. It's pretty much empty. And that is why we call the space a pretty empty space. However, all these things that we're looking at from the Milky Way, the Andromeda, and all this galaxy you're looking at right now, only made up about 5% of our universe. These are the visible matter in the universe. The remaining 95% are things that we don't really know what they are. About 27%, we call them dark matter, which will be the main topic of today. And the rest, 68%, we call them dark energy. So I should make a few clarification here, important clarification. We call them dark matter and dark energy, not because they are dark. They are dark in some sense, but I guess it's better to just call them invisible. So they are not dark in terms of they are black. They are dark just because we cannot see them. They are also dark in a way that they are mystery to us. And I should say, just because they both have dark in their names, They pretty much has nothing to do with each other, with the exception that we have no idea what they are. We do know that they are different, which I will go into later in this talk. But other than that, they are pretty much mystery to us. So now imagine the picture that you saw earlier with all the galaxies. What if you can see dark matter? As I mentioned to you, dark matter is invisible. But if you were able to see dark matter, this is what the universe will look like. You can see it's a lot more interesting than just the galaxies. We see all this web structure in the universe. We call it the cosmic web. All this web are actually dark matter. They are dark matter forming thin filaments in the universe. Dark matter are massive. They have gravitational pull onto each other and onto the normal matter or visible matter. And so they pull visible matter and normal matter together and form a deep gravitational well. So basically a high density region of dark matter. And then stars and galaxy forms within those high density region. Across the high density region is the web that I mentioned about. So this is a static picture of the universe with dark matter being visible. So now let me play a movie of how the universe evolved when you look at the dark matter component. I understand that through Zoom, this could be a little bit choppy, but hopefully you will start to see from a very dark, the dark matter being very uniform distributed, you start to see contrast. You start to see the filament being formed. And that is because the gravity pull dark matter together, and the denser region become even denser because of the pull of gravitation. You can also see that bright spots. All the bright spots you are looking at here are actually just high density region. It's just that the way that we color the density. But it is at this high density region where the galaxy and the star form. The hydrogen gas in our universe are being pulled by this high density gravitational well at the center of this density peaks. When the density becomes high enough, they ignite the nuclear fusion and the stars form at those density peaks. And then more and more stars form, and then they become galaxies. So that is basically the galaxy formation 101, how the galaxy forms through the evolution of the structure of dark matter. So I kind of already tell you what the cosmologists have known since the past, I would say, 3 decades. But how do we actually know galaxies live inside this dark matter? We call it halos. This is the jargon. The term halos here merely means this high density peak, the high density peaks that you saw in the earlier movie. How do we know galaxies actually live there? Why we know that dark matter are the invisible nests of the galaxies? So I will start with this quote from Friedrich Bessel. This is in his letter to Alexander von Humboldt in 1898. He says, the visibility of countless stars is no argument against the invisibility of countless others. This quote is, in the context of this quote is when they are discussing Sirius, actually. They notice that one of the stars in the Sirius have a small perturbation as a function of time. It's not like sitting at the fixed point. And so the question, what could be the reason for that? And so Friedrich Bessel proposed maybe there's a companion star that is too faint to be seen. So you have a brighter star and you have a very faint star that is nearby. And because of gravitation effect, these 2 stars are orbiting each other. And that's why you see a small wobbling of the brightest star, even though you cannot see the fainter one. And it turns out this quote actually applies very well to how we discover dark matter. So I showed some equations, but the equation really is not important to the context of this talk. But I do want to mention that through the Newtonian, like Newtonian physics, law of physics, we were able to infer mass from motion. So if there's one object orbiting the other object, the faster this smaller object is orbiting means that the central mass of the center object must be much higher. There's a mathematical relationship between the velocity of the orbiting velocity and the mass of the central object. And so if you were able to observe the orbiting velocity you can infer the mass of the enclosed, the mass enclosed by this orbit, basically. So what people have done is to measure the velocity of the star orbiting a galaxy. So remember, this is a Milky Way-like galaxy. It's not a Milky Way, but it's a spiral galaxy. And so all the stars on the spiral are orbiting around the galaxy. And supposedly by measuring the velocity, you were able to infer the mass, we think. Astronomers are using something called a Doppler effect to measure the line of sight velocities. And basically, this is how like the speed radar gun works on the highway. When you are moving and then we shoot a light toward you, the reflected light will change its wavelengths based on the speed of your car. And so similarly, when the star is moving, we can measure the velocity by measuring, we call something called the spectra of the stars. So with that, we can measure the velocity of the stars across this radius of the galaxy. So here I'm showing you the actual measurement done by Vera Rubin. The y-axis here is the rotational velocity, how fast the star is moving. The x-axis here is the distance from the center of the galaxy. So 0 means at the very center of the galaxy. 25, this is in kiloparsec, so which is about 75 kilolight years, is around here near the boundary of the galaxy. And you can see that the star is pretty much stationary near the center, and then they become much faster. And then the velocity kind of stay at the fixed velocity across the galaxy. All the different lines are measurement from different galaxies. So I just told you that the velocity we see here can use to infer the mass of the galaxy. There's another way to infer the mass of a galaxy that is from the light. So you basically now have two ways to measure the velocity. You can use two ways to measure the mass. You can use the velocity that you just measured. You can also use the light that you see from the galaxy itself. The galaxy light is usually modeled as an exponential disk. So you have a much larger light here at the center, and then you kind of exponentially decay through the outskirts of the galaxy. And you can do an integration, and then you get the mass enclosed being this formula, which is, again, it's not important how the formula actually means, but basically this formula means what is the mass enclosed as a function of radius. So now we can plot this. This formula gives you this blue line you see here from the visible matter. This is the expected rotation velocity from the visible matter that we see here. This is the observed rotation curve from the previous slide. Remember that things goes up and then kind of flatten out. So this means the stars are orbiting much faster than what we would expect if there were only visible matter that we see on this plot. And that difference means there must be some other mass, we think, or the Newtonian law is wrong. And so if you choose to believe Newton's law, then the only explanation is that there's some mass that you cannot see in here, so that the velocity can be much higher near the outskirts of the galaxy. And that thing that we don't see, we call it dark matter. And that is basically how people discover dark matter and being convinced that there must be some matter that the galaxy is seizing in order to see the velocity. So I will pause a few seconds to see if there's any questions so far.
No, we're no questions as of yet.
Oh,
Great.
actually, I have a question.
Sure.
From the cosmic web from the video, I was wondering, is there any indication that that cosmic web is layered?
Great question. So depends on what you mean by layers, but the cosmic wave you see here, they can intersect with each other. So it's a little bit different from regular web. The dark matter filament that you see here,
yeah,
they can penetrate each other without pretty much being affected. And so you can see some of the region, like denser region, they are actually intersection of many filaments, many dark matter filaments, and become a much denser region at the center of the intersection. I don't know if that's what you mean by layered.
Yes, and I was wondering if radially there is a connection.
Yeah, I see. So dark matter is kind of more like a fluid, if you will.
Mhm.
So there is a density gradient from the center to the outer region. And you do see sort of like this boundary, like this is more kind of like a, if anything, is like a shock wave kind of thing. So you can say it's layered, but it's more like a layer of fluids. So if like ripples on the water, if you will, rather than layers are seen closest.
I see. Thank you.
Yeah, no problem. Okay, so so this is one evidence of dark matter, but I should quickly go through a few others because this is not the only evidence of dark matter. The reason that most of the scientists, I would say probably 95% of astronomers, are all believe in dark matter being exists, despite that we have very little knowledge about what it is. It's because there's multiple evidence pointing to the existence of dark matter. So besides rotation curve, there's something called gravitational lensing. So you're looking at a large galaxy here. And what you can see an interesting behavior is you see this arc structure. If you look at my pointers, you can see several arcs surrounding the galaxy. You can see a few more here. You can also see some of the arc structure here. The arc structure you're looking at is something called the gravitational strong lensing effect. This is because the mass is when it is heavy enough, it can actually bend the light. So when we observe a galaxy cluster, which is like this block corresponding to this galaxy. And if there's other galaxy behind that large galaxy, the galaxy behind its light will bend by the galaxy, pretty much like a lens. That is why it's called gravitational lenses. And then reach Earth from many different angles. And that is why you see like an arc structure. That is the light from the galaxy that is being bent through many different angles and reach Earth at the same time. But how much the light will bend depends on the mass enclosed as well. And so by measuring the radius of this Einstein ring, this is the name of this ring is called Einstein ring, we can actually measure the mass within. And then again, we find the mass is much heavier than the mass from the galaxy itself. And so that's another evidence of dark matter. Yeah, another evidence coming from something called the cosmic microwave background. So this is the kind of the light from the very early universe. So you are looking at the illustration of the history of the universe, starting from the Big Bang, and then the inflation happens. And then the first star formed about 400 million years ago. And then gradually the galaxies start to form. Now here is one place I want to distinguish dark matter and dark energy. Earlier in the movie, you see dark matter did one thing. They come close to each other and form high density regions. So if you think about dark matter, I want you to think about they pull things together. So galaxies could form because of dark matter, because dark matter pull gas, the hydrogen gas together, and the star could form. And then they pull more stars in together, and the galaxy could form, etc. Dark energy, on the other hand, when you think of dark energy, you think they push things farther away from each other. So dark energy is the reason why the universe is expanding, actually expanding acceleratively. And so this is the accelerated expansion that you see here, and that we attribute that to dark energy. So again, dark energy and dark matter, even though they have similar names, they pretty much has nothing to do with each other. They actually have pretty much the opposite effect in terms of the evolution of the universe. Now, precisely because they act very differently, we can then compare late time universe and early time universe and actually derive how much dark matter and dark energy there must be in order to see our current universe. So you can imagine if our universe has a lot more dark energy, but much fewer dark matter, then our universe will actually be expand so fast and the galaxy don't have time to form. There's nothing pull them together. Similarly, if we have a lot more dark matter, but much less dark energy, then we should see a lot more galaxies than what we see today. And so this is a way that we can estimate how much dark energy and dark matter there should be. And so when we look out to the cosmic microwave background, all this perturbation that you are seeing here give us a hint of the ratio of dark matter and dark energy. And so in fact, the pie chart I showed at the very beginning of the talk, the reason that we have this precise measurement of how much dark matter and dark energy there must be in the universe, coming from measure the fluctuation that you see earlier in the cosmic microwave background, or CMB. And you don't really need to know what the units or numbers mean here. This is basically a way to measure the perturbation. You just see a 3D map, 2D map earlier. There's one way to represent the perturbation on 2D map in this plot. And all the measurement is the points. And the red line is when you assume this composition of the universe, then how much fluctuation you see in that map. And so this just demonstrates that the reason we have this precise measurement is because we have a precise measurement of the cosmic microwave background. And you can see the theory prediction match the data points very, very well. There are many other evidence pointing to the existence of dark matter that I'm going through today. So I basically talked about 3 evidence that I think are most important: the galaxy rotation curve, gravitational lenses, and the cosmic microwave background. But we don't really know what dark matter is. Through this evidence, we know that dark matter is not any matter that we already know about. It's not light, not atoms, not electron, etc., not neutrino. We also know that dark matter hardly interact with anything we know. So they don't bounce off light, they don't bounce off regular matter, they don't absorb or emit light. And that is also why when I say dark matter is a little misleading, because for something to be dark, you need to absorb all the light. But dark matter didn't even absorb light. Light would just pass through dark matter without any interaction. In fact, the dark matter particle probably are penetrating us right now at this moment that we cannot feel it at all. It doesn't have any interaction with anything we know. Regardless, we're still working very hard to try to find out what dark matter is. Even though dark matter hardly interact anything we know, we have this very kind of the last hope, hoping that dark matter will, in some very tiny chance, interact with something. And so we have several experiments in this very cute cartoon. It actually nicely depicts several experiments that we are running, scientists are running to find dark matter. This one is called a direct detection experiment. This is putting a detector very deep underground. And because dark matter doesn't interact with anything, dark matter will just penetrate the Earth. And we hope at some point it will hit the detector and have some tiny chance that interact with the nuclei within the detector and give us a signal. All other matter that won't even hit the detector because they will be shielded by the Earth. This one you see here is called indirect detection. This one is hoping that the dark matter interact with itself. And maybe there's some chance the 2 dark matter particles will collide with each other and annihilate and create gamma ray. And so we have gamma ray telescope there trying to monitor if there's any annihilation from dark matter particles. This one you see here is called the collider. This, for example, the Large Hadron Collider, LSST at Geneva. So in this case, we are smashing particles, known particles like protons together. And hopefully it creates a large enough energy that actually produce dark matter particles through energy. As we know, the energy and mass can transfer to each other. So all these different methods are ways that we're trying to find dark matter through waiting there for dark matter to hit, waiting for dark matter to hit each other, or actively producing dark matter. So have we found dark matter yet?
Can I interrupt? We got 2 questions from YouTube.
Yeah.
So the first one goes back to a little bit earlier with the cosmic web. The question is, just to make sure I'm understanding, the cosmic web is actually sort of an inverse web, since it's defined by the space between the streaks made up of dark matter, right? And that the streaks would be the absence of dark matter.
Yeah, very good question. So the web you see is the existence of dark matter. And so if the galaxies are, if you can see the galaxy as well, galaxies will live in all these bright spots, basically. And so when dark matter is not visible, this is what you see. And what scientists are trying to find is to see if there is a high density region, even though you cannot see anything in between these two galaxies, for example, just as an example. And so there are other things we can do, like gravitational lensing we just mentioned. So we can measure if there's any mass in between, even though there's nothing we can see. And indeed, we see some of those things. So basically, there's dark matter filament that is connecting this galaxy that we cannot see. And for regions, there is very low density of dark matter. So in this plot, in this plot, the dark matter is actually dark. All the white space, they are basically low density or underdense region of the universe, where we call them voids. And so the cosmic wave is basically a dark matter filament surrounding the voids. Within the voids, there are very few galaxies or even very few stars, because as I say, the star need to form within the high density region of dark matter. So I hope that answers your question.
The next question is, am I correct in understanding that stars in the outer edges of the spiral galaxy revolve around the galaxy center at the same rate as stars orbiting closer in? If so, why?
Yeah, very good question. So indeed, as this plot shows, the stars in the outer region of the galaxy are roughly here, orbiting roughly at the same velocity to the stars orbiting here. Obviously, when you go to even inner regions, things start to, the velocity start to decay. And the reason why the velocity is similar here and here is exactly because the existence of dark matter. If there were no dark matter, it would be the blue line, where the velocity would decay near the outskirts. But because the existence of dark matter, there is a lot more mass than we can see from the galaxy. And when there is a stronger mass, there's a stronger gravitational pull. And when there's a stronger gravitational pull, the rotational velocity needs to be faster from Newton's law. Or you can, if you can see this equation, if you have more mass within a certain radius, then the velocity, rotation velocity at the radius needs to be higher. And so because the existence of dark matter, it happened to be there, it's more like a coincidence. Like there's no reason that this must be flat. But it just happened to be because of the distribution of dark matter and the distribution of the galaxy light. The velocity, rotation velocity is roughly flat near this outskirt of the galaxy.
Go
ahead, John. I have a question.
Can you hear me?
Yes.
Yeah.
Oh, okay. I just have a question concerning the expansion. Let me see how to explain it. And I don't even know how you figure it out. But when we look again at the filamentous structure of the universe and the dark matter, and you superimpose the expansion on that, are the areas, the nodes, which contain more mass, are they expanding for the same distance? Are they expanding at a slightly different rate than material next to them at the same distance? Are they moving faster? In other words, is the expansion the same for any particular distance?
That is a great question, right? So basically, or let me frame it in a more dramatic way, if you will, the expansion rip the galaxy apart, right? Because there you can imagine two scenarios where the expansion, the galaxies between each other move away from each other, where the galaxies stay intact. Or you can say maybe the expansion is so fast that the galaxy itself will be ripped apart. So that again depends on the ratio of dark matter and dark energy. The expansion itself is pretty much homogeneous. So expand from every direction, every point in the universe, you roughly have the center of expansion. But the dark matter near the galaxies also have a very high density region and pull things within each other. So the expansion of the space is still the same. But because the gravitational pull, things will be putting together just because the gravity like kind of pulls things together. If there are fewer dark matter, then actually the galaxy could be ripped apart. The current ratio of dark matter and dark energy is kind of a very nice number, so that the galaxy won't actually be ripped apart as the universe evolves. But galaxy and galaxy, they will be moved away from each other further and further away. In a very distant future, we basically cannot see any other galaxies. All the galaxies will be moving outside of our horizon. But we can still see everything within our galaxy because the dark matter kind of keep the stars within the gravitational well.
Okay, we got just another quick question from YouTube. If dark matter doesn't interact with anything, how can the detector detect a small mass, weak gravity, dark matter particle?
Yeah, great question. So when I say dark matter hardly interact anything, this is as far as we know. And so basically all these things you can say kind of like we are hoping it will interact. And if it does interact, then we have a small chance to detect. If the dark matter really never interacts, then there's no hope. We basically have no way to find dark matter through any of these methods. So this is kind of, so we kind of hope that dark matter have some amount of interaction, even though very small, and we hope to detect it. And so that actually nicely brings back to my question, have we found dark matter yet? And the answer is that with all these three methods, we haven't, in the sense that we kind of set the upper limit of how much the interaction could be, right? Because when you didn't see a signal, it must mean that dark matter cannot interact with normal matter at a rate higher than a certain number. Because, right, if it has the interaction rate much larger than that, we must have seen it. Kind of the logic is kind of like that. And so when we say we haven't seen dark matter, we basically say the chance or the frequency that dark matter interact with normal matter or even interact with itself is much, much lower. And as the precision of all these experiments become higher and higher, we just push the limit into a lower region. And dark matter, basically we can conclude that dark matter is less likely to interact with normal matter. But I should also say, if you like dark matter, like I do, you can actually buy dark matter from Particle Zoom. I actually have one myself. So that is one way you can find dark matter on the internet. So from there, it sounds a little bit hopeless that we couldn't find dark matter through all this experiment. And so the rest of the talk today, I want to give you a sense of hope. To ask this question, are there any other ways that we can learn more about dark matter? So even though we don't know what dark matter is, it doesn't prevent theorists to come up with models of different dark matter. So in all these different cartoons, you are looking at the proposed possible dark matter composition. You don't need to care about all these different names. But this cool cartoon actually demonstrate why they are different. So some of the dark matter model are things that they don't really interact with each other. Some may have light interaction. Some like to interact with each other. Some are composite. They actually look like they actually composite by very smaller particle and look like a large dark matter particle. So the question that we are asking is that there are so many different models that people propose that dark matter could be, but we haven't detected any of them. Is there any other way that we can still distinguish some of these models? So that brings me to my own research. My research is trying to understand the connection between this underlying dark matter model, dark matter structure that we saw earlier, to the visible galaxy. The dark matter is actually a very simple thing. They only interact gravitationally. And it's closely related to all the theory I just showed you earlier. So they are very easy to simulate because we know gravity very well through Newton's law. And so their dynamic or their motion is mostly well understood. The galaxy, on the other hand, they are very rich in their properties. You can see all these different kind of galaxies. They have different color, different structure. They have a different amount of mass in them. And we also live in one galaxy, right? The Milky Way galaxy ourselves. And so if we can understand how the galaxy connect to this dark matter structure, maybe by observing the galaxies, we have some way to actually make this plot, right? This plot that we are looking at, this dark matter web structure, is from simulation. But if there's some way that we can understand the connection, maybe we can actually draw the dark matter map from observing the galaxies. And so before I go on, I must make a very important point about the scale. So here I just point the dark matter clump to this galaxy. But I want to highlight the scale we are talking about is very different. So on the right, you're looking at the Milky Way-like galaxy. The radius is about usually, I would say, at most 100K light years. And that compared to the clump of dark matter is really, really small. So usually the clump of dark matter halo, that's what we usually call this clump, hosting a galaxy like this. The radius is about 10 or 15 times of the radius of the galaxy itself. So the dark matter halo is much larger compared to the galaxy itself. And here's just some nomenclature. For theorists, we like to think everything spherical. And so we usually call this dark matter halo, even though they don't look spherical at all, we just call it like a spherical dark matter halo. And as I told you earlier, the galaxy live at the very center of the galaxy. And you can see some other kind of high density peaks, right, within this halo, and we call this subhalos. And there will be some smaller galaxy living in those subhalos. It's not super important to memorize these terms. It's just helpful for me to use in the rest of the talk. So if you remember this plot from earlier, this shows you local group, right? So now maybe you can understand why there are so many galaxies orbiting the Milky Way and there are so many other smaller galaxies orbiting the M31. There is basically this picture that you're looking at. This, there is actually invisible dark matter halo surrounding the Milky Way. And remember, it's much larger, right? The radius is about 10 times of the Milky Way disk itself. And there are many smaller clumps in that dark matter halo, which we just call them subhalos. The subhalos are where these smaller galaxies are hosted. We call this smaller galaxy satellite galaxy. And we use the term satellite just because the small galaxies are orbiting the main galaxy. So it's kind of like the satellites orbiting the Earth. So satellite galaxy, the satellite term here really just means something that is orbiting the other thing. And so there are the galaxies living in the subhalos that you see here earlier. And this will be the Milky Way galaxy. And so here you are looking at two main halos, one main halo here with many subhalos within, and the other main halo here with many subhalos within. And this two main halo is called the local group. So why this is important? Because it turns out with all these different dark matter model I showed you earlier, that actually impacts all the subhalo and how they distribute. So you are looking at three different dark matter model, the cold dark matter, self-interacting dark matter, and warm dark matter. The warm dark matter is really visible, the difference, right? You can see much fewer substructure or much fewer subhalos. And so with much fewer subhalos, it means that there should be much fewer satellite galaxies. The self-interacting matter is a little bit different to see by eye, but you can actually see there's a less dense core at the center. And actually, there is also a fewer substructures. It's a little bit different to see, it's more subtle. But again, the small scale structure or the subhalo can be used to distinguish different type of dark matter models. So from there, we can come back to our Milky Way. So here's another plot of the Milky Way and satellite galaxy. The Milky Way galaxy at the center. All these other plot points are the satellite galaxy. You can see LMC here, SMC here. This is just like an illustration. If we compare this with the dark matter distribution, and we ask, is this a realistic representation of this dark matter distribution? If it's not, then maybe we need to change the underlying assumption of what dark matter is. And so that is the basic line of my research, trying to study this kind of satellite system to understand whether this is consistent with our picture of dark matter. Now, obviously, there is a small difficulty here. That is, there's only one Milky Way, the one that we live in. And how representative this really is, we don't really know. And so for that reason, I have been working on something called the SAGA Survey. And this, the SAGA stands for Satellites Around Galactic Analogs. So this survey is looking for satellite systems similar to the Milky Way. So here's an example. This is a Milky Way galaxy. And we are trying to look for the satellite around it. Remember, the satellite distribute around the galaxy. They are much further spread out, right? This is kind of the dark matter halo that is hosting the central galaxy here. Remember the scale that I showed you earlier. And so we go out and look for many this kind of Milky Way galaxy and try to map out the satellites around them to give us more Milky Way-like systems that we can use to study dark matter. I'm going to skip that. And so far we have found so many satellite galaxies. So here you're looking at actually kind of the census of satellite galaxies of 36 of Milky Way siblings. In each case, the Milky Way-like galaxy is at the center. You can hardly see it, but in some cases you can, right? There's a black spot there. That is the central galaxy. And the color circles are the satellite galaxy that we identified within the dark matter halo. The dark matter halo is roughly this large circle that you see here. And so you can see in some systems, we find like 9 or 10 satellites. In some systems, we find like 1 or even 0 satellites. And again, the number of satellites tell us something about whether this is consistent with our prediction from the dark matter model. Here's just a different view. So far I've been talking about in numbers in a very abstract form, but all these satellite galaxies, they really exist. And so I'm showing you the picture of a satellite galaxy. They are very bright galaxies. They are really faint, fuzzy, small galaxies. And you can again see in some systems, you have like 9 or 10 satellite galaxies. In some systems, you have 2, 1, or even no satellite at all that we have found so far. And so if you now start to count, like I have 2 systems with no galaxies, no satellite galaxy. We have 3 systems with only 1, 3, 4 with only 2. And if you just do this counting, you can make a plot like this, the number of satellites per system, and then you can count how many systems that you found with that number of satellites. And then you can compare it to your dark matter simulation that we ran. And so the stars you see here are what we found in our survey. And the bluish band is what we predicted from the cold dark matter model. And so this is telling you so far from what we can find so far, they still seem to be consistent with each other. There's no clear discrepancy between what we observe in the SAGA survey and the cold dark matter model. Now, obviously, you can see a lot of large error bars, and you can see the prediction is also not very narrow. You can imagine that if we were able to observe a lot more of this kind of system and also run more simulation, you will tighten the error bars here. And then maybe we can see some discrepancy, or we see no discrepancy. In both cases, they are interesting. In addition to numbers, the spatial distribution of a satellite can also help you to distinguish different dark matter models. So here I'm showing again 3 different dark matter models: cold dark matter, warm dark matter, self-contained dark matter, and also show you a case which with cold dark matter by you adding the galaxy disk into your simulation. And you can see the satellite, which is the colored points. They all have slightly different spatial distribution. They have different numbers, as we discussed earlier. For example, warm dark matter have a lot fewer satellite galaxies. They also have different spatial distribution. So understanding the spatial distribution of satellite also provide information to distinguish different dark matter models. But as you can see here, this particular exercise require you observe a lot more satellites, right? You need to see for this kind of distribution, tens of satellites. Like in the SAGA survey, we only find like 3 to 4 satellites per system. And so you ask, what does it take to see more satellite? As you all know, the further you look, you cannot see fainter objects. You can only see fainter objects that are nearby to us. So in the Milky Way, we can find a lot of satellites because they are so close. We can find very faint satellites in the Milky Way. So in the Milky Way, so far we find about 60 satellite galaxies in the Milky Way. In the M31, which is our close neighbor, even though it's still very close, we can only see about 25 satellites in there. That doesn't mean they actually have fewer satellites. It just means you have some satellite that is faint enough that we cannot see at that distance. The SAGA survey is even further. And so we only can see 3 to 4 satellites in the SAGA, each system in the SAGA survey. If you go to a different survey, the Scone Digital Sky survey, that has it goes out to even further away in distance, about 200 megaparsec. And you can see even fewer satellites because, again, the brightest or luminosity limit that you have is even brighter. And so you can only see like 1 or 2, the brightest satellite in those systems. So in order to do the exercise I mentioned, like get more satellites, what we need is a deeper survey or a more powerful telescope. And so you can see much fainter, so that at the same distance, you can probe more satellite at the same distance, go to a fainter magnitude limit or fainter brightness limit. And so I'm just at the very end of my talk mentioning large astronomical survey that I've been participating. On the left, this is the dark energy spectroscopic instrument at Cape Pitt in Arizona. So this is a spectroscopic survey, and a spectroscopic survey means that it can measure the distance information. So similar to what we did in the SAGA survey, you are measuring the distance of a galaxy and see if the galaxy live close by or far away. And so here you can look at a picture. In the field of view of this telescope, it can put 5,000 fibers in the field of view. It means that it can measure 5,000 objects distance at once. And so this is a very powerful tool that will map out about 1/3 of the full sky, measure distance to billions of objects. And the first year survey actually just started on Monday this week. So I'm really excited about this survey. On the right, you're looking at the Rubin Observatory. They are running a survey called the Legacy Survey of Space and Time. So this is a telescope in Chile. Now, the Rubin Observatory is an optical photometric survey. And by photometry, it means that you only take a picture. So you don't have the distance information. But the LSST is a lot more powerful, excuse me, than the telescope using DESC, which means it can go to even fainter distance or fainter magnitude limit. You also have the largest digital camera that have ever been constructed. And here you are looking at the picture of Rubin, and this is taken by this 3.2 gigapixel camera that is already being built for the Rubin LSST. The telescope is currently being constructed, and it will go online in about 2 years. And this will be our future flagship astronomical photometric survey in years to come. So I'm really excited with these data sets. And within the Rubin Observatory community, I have been leading something we call the Dark Matter Working Group within the Rubin Dark Energy Science Collaboration. And I'm not going to detail of this slide, but I just want to say we are basically planning for what we can do with the Rubin Observatory to try to understand the nature of dark matter. And then including things like measuring the smallest halo mass. Again, you need to have a telescope that can go to really, really low luminosity limit in order to measure the minimum halo mass, right? Because the smaller galaxies live in smaller halos. And so this is one of the examples of why a future survey will help us to understand dark matter. So with that, I will just leave my summary slide here. I hope you will learn today how the galaxy connected to the underlying dark matter structure, and how by learning more about these little galaxies orbiting around Milky Way and other Milky Way galaxies, we can learn more about the nature of dark matter. So thank you.
And we have a few questions that were posted on YouTube. So one of them, as a follow-up question of detection, could you please give some example of candidate detectors are using now?
In terms of the, I assume this is the direct detection. So the detector here is usually, there are many different kinds, including the most famous one is probably the xenon. So this xenon is a noble gas. So you basically put tons of xenon gas in liquid form. And because they don't interact with each other, right? Xenon is a noble gas and it doesn't interact with other thing else. But when dark matter particle hits a xenon nucleus, it will create a small energy burst and creating electron and light signal. And then you basically have kind of like camera, it's not actually camera, but you have something to detect the electron or light signal through the interaction. And other than xenon, there's also other things like germanium. I think, yeah, xenon, I'm trying to come up with other different, there's a few semiconductor type of detector as well. This is also similar to neutrino detector. Usually neutrino detector use water, a large water tank. And again, you are waiting for the neutrino to hit the water atom to create a signal.
Okay, we have how is the detailed structure like the halos and the subhalos of dark matter mapped? Is it through gravitational lensing?
Yeah, great question. So, the map that you're looking at in most of my talk are simulating the map. So this is, we assume dark matter exists, and then we put in the right amount of dark matter and dark energy, and then the universe evolve, and that is how we create this map. In this kind of, if you ask observation, how do we find this halo? We can find halo. We do through gravitational lensing, as I showed you earlier, like this. This is basically a dark matter halo at the center, or through rotation curve. Again, this kind of a dark matter halo. To find a subhalo is a lot more difficult because the subhalo is much smaller, and the kind of just a perturbation to the halo is much massive, right? And so you can imagine if you have a subhalo here, it doesn't change the line too much. But people have been doing that. This is an active research area trying to use gravitational lensing to observe substructure. So the idea is that if you have a substructure, you will see a small perturbation on the arc. And so by modeling the small perturbation on the arc, you can try to detect the substructure or subhalo using gravitational lensing.
Are there any targets an amateur astronomer can capture that would be an example of dark matter existence?
So I guess gravitational lensing is one of the possibility. I think is still very difficult for most amateur telescope because the contrast is very large, right? Usually the central galaxy, that you need to have a very massive galaxy in order for gravitational lensing to happen. And so this would be very bright. And then the arc would be much fainter compared to the central galaxy. So I'm not quite sure if this is possible captured by amateur telescope, but I would say this is one possibility. All the galaxies you're looking at, basically, you are looking at actually existence of dark matter. There's another evidence I haven't mentioned. The fact that this kind of disk galaxy can exist, this very thin disk galaxy, it actually is not dynamically stable to have a thin disk unless it's living within a much larger gravitational well. And so the fact that the existence of this very thin disk galaxies actually is also evidence of dark matter. But otherwise, you need to be able to measure the rotation velocity to actually see this kind of plot. And I think spectrograph is usually not available for most amateur astronomer. But observing the disk galaxy itself, you can see that as evidence of dark matter.
And is it possible to learn something useful by compiling composite satellite data from multiple galaxies?
Yeah, so I guess if I understand the question correctly, you are asking kind of stacking the satellite together. So we observe many different systems, and we kind of find a way to combine them. And the answer is yes. And we have been trying to do that. So this is just one of example which we analyze each satellite system as individual satellites, individual systems. But for example, if you want to do something like this, there's a way. So I didn't explain this fully, but you can see there's a line here. This highlights the most massive satellite in that system. So the idea is that if you orient each satellite system so that their most massive satellite aligns, and then you can put them together. Maybe you can use that as a way that even though you don't have so many satellites in one system, but you can use that as a way to look at the spatial distribution to see if there's any signature. So this is actually something that is being active developed and researched on. Great question.
Okay, that covers anything from YouTube.
Thank you.
Thank you very much. It was extremely interesting and informative. I have to believe that when the LSST comes online, it's going to everybody's thinking that there's going to be some new breakthroughs with the quantity and quality of data that they're going to be able to capture. I'm hoping we get there very soon.
Yeah.
Sooner than later.
Yeah, I mean, actually, things are happening very fast. I mean, from the outside, it probably seems like this has been there for a while, but we are actively preparing for the arrival of data. The sheer amount of data is really unprecedented, and a lot of infrastructure need to be worked out before we can actually meaningfully use the data. So right now, it seems like the first flight will be coming in 2023. It has been delayed for a year due to the pandemic. But we are actually working really hard right now to make sure we have a data transfer pipeline, data access pipeline, so that we can kind of start to do science when we have the first flight.
Yeah, as I recall reading some of the information about the construction, they literally have to create a new international fiber network to port all the data, which is extraordinary. I think they're talking about petabytes, if not maybe less than that each night. But it's going to be an incredible feat to distribute it and store it. Yeah. So we need to find out the companies that are going to be making the storage devices so we can make some investments.
Yeah, in fact, one of the most stringent requirements for LSST is that the data taken in Chile need to arrive in the US within 6 seconds. And that is for many reasons. LSST is great for galaxy science that I mentioned, but it's also great for supernova science, which you need to be alert when something happens. It's also used to monitor near-Earth objects, and you really want to be alert if something is going to hit the Earth. And so there is actually a requirement that the data need to be going to US data center within 6 seconds. And that is why they need to build a specific network line between Chile and the US for that to happen.
Yeah, that's remarkable. I didn't, when you think about all the different types of sciences, that's, projects just going to be performing all the time. It's going to be huge benefit to the astronomy industry for sure.
Yeah, and the best thing is that the LSST data will be freely available to everyone in the US and Chile. And so it will be really transformative compared to previous astronomical surveys.
Great. Well, thank you.
Normally, you would be invited because you're nearby to our observatory to conduct a presentation, but unfortunately the pandemic has erased that. But we once we get open again, we wish you would stop by and visit and see our facility.
Yeah, I look forward to be able to visiting.
Yes.
Yeah, we look forward to that. We had, Len, am I correct? We had 23 viewers on YouTube at the same time?
We had up to 28 for a while.
Okay.
That actually went up to. There was just one person who was asking, since you were talking about with the 6 seconds, why 6 seconds? Is it for just because of like you were saying, for watching for supernova and near Earth objects, or is there any other specific reason?
Yeah, that's the two things I think most. I mean, there is a class of objects called transient events, that including supernova, near-Earth objects, and other things, other unknown transient objects. I don't know exactly how they derive 6 seconds, this number, but basically this is a community requirement. They basically make a code to all the astronomy community to say like how fast you need to get the data before you can do follow-up. Because sometimes there's an important event that you need to point out the telescope at the location. And so there is a pipeline, right? Basically you see something weird happening, and you analyze the data very quickly, and then you send out a code to all the other telescope on Earth to say, look at that direction right now. And that is how they come up with the number 6 seconds.
Is it actually then, is in Chile, are they doing any analyzing of the data when it's being done? Like to say, we recognize a supernova, so that something else can be,
So I think that analysis happen at the US data center.
Yeah,
So
okay.
the data goes from Chile to US data center, and then they do this, they
And
call
it's-
the alert system, broker system. They basically look at any like strange time series objects and then send out alerts to everyone to say, hey, there might be something happening.
Well, we just had somebody post, they wanted to know when your next episode of Dark Matter was going to be.
Very good.
And that's it for questions on YouTube. And if anybody else on Zoom have any questions, please ask.
You guys gonna mute yourself, show your video, or any or all the above? Looks like it's a wrap, Len.
Okay, I'm going to kill. Thanks everybody for that was on YouTube watching. We're going to kill the live stream now.